Now we'll start talking about how to display categorical data. As you recall, categorical data can be summarized as it can be binary data, it can be in multiple categories, and we're talking about categories, so it comes red, blue, yes, no, there's no in between, pregnant, not pregnant. Any of these kind of things where you have you have multiple categories, but there's no in betweens. There are three different primary ways you can display categorical data. You can use bar charts, pie charts, or tables. There's other ways, but they're not as common. Bar charts are usually preferred over pie charts simply because they're easier to visualize. It's easier to grasp how different the different bars in the chart are. In pie charts, if it's a simple pie chart, it's usually not a problem, but when you start getting a complex pie chart, such as this pie that's been used to display the government budget, it can become very confusing and trying to determine just how much bigger or smaller one of these little slices are than the other. Tables are great because they show lots of detail, but often tables become confusing and cumbersome to work with, and you can't just glance at a table and get the big picture. Oftentimes you might have to study the table for quite a long time to get the big picture. So depending on what you're trying to say with your data will determine whether you use a pie, a bar, or a table. Sometimes it's not so important what your pie chart says as whether or not you have whipped cream. Looking at a table here just to display what I'm talking about, if you look here in the left-hand columns, your categories, and then you get all these different numbers. It's hard to compare these numbers back and forth when you just glance at them, and I think that you can see that very obviously in this picture. One thing you need to recognize is that a bar chart is not a histogram. A histogram is used with continuous data where you make artificial categories. A bar chart, there's spaces between the bars. There's also another sort of mixed graph called a clustered bar chart, which might work like a series of little histograms or a series of bar charts, and that's on the right here. You probably aren't going to use those very often unless you have fairly complex data, in which case they can be very useful. But bar charts are what you see on the left, and I just want to make sure you don't get them confused with these other types of charts. I've made mention so far about normal and non-normally distributed data. It's important that we discuss this now. Normally distributed data is what you think of when you think of a bell curve. There's just as much data to the right of the mean as there is to the left of the mean. In the below figure, you can see a bell curve, and you see that this one has standard deviation showing. And as you see, the data spreads left and right at an equal rate. So, and in the case of a normal curve, you're going to have the mean, the median, and a single mode all in the same place. And in this case, it's at 0, but it doesn't have to be at 0. It's just so long as you've got everything distributed in a bell curve. As we all know too well, not everything is distributed in a bell curve. Here we have a comic that shows one person who makes a lot of money and everyone else that's broke. And of course, the average comes out to $50,000. Well, this is a skewed distribution of wealth, and we need to understand how to describe that as well. Here we have two different distributions. One is a negatively skewed data set and the other is a positively skewed data set. When we say something's skewed, that means that the extremes, the tail is longest at the positive end, not that most of the data is on the positive end. That's real important to recognize. When you have a positively skewed data set, most of the data is in the smaller numbers, such as shown on the right. We say that the tail is skewed to the right. Here, if we were looking at rich and poor, we'd have in the positively skewed distribution, there'd be very few real super rich people way at the extreme, and then a whole bunch of people that fall down at the lower end. The opposite is true of a negatively skewed data set, which we see on the left. In this case, there are very few very poor people and lots of real rich people. Wouldn't that be nice? When we look at skewed data, we can look at the relationship of the mode, the median, and the mean, and that will tell us something about how the data is skewed. If we look at a distribution where the mean, median, and mode are all on top of each other, we're looking at a normal distribution. There's no skew there. If we have data that is positively skewed, then the mode will be to the far left, the median will be somewhere in between the mode and the mean, and the mean will be to the right of both the mode and the median. Likewise, in a negatively skewed distribution, the mode will be to the furthest to the right, the mean will be furthest to the left, and the median will fall somewhere in between. We've mentioned three terms, the mean, the median, and the mode, so far in this lecture, but we haven't really defined them. When we take the mean is that average you've done with averaging your grades in a class or things of that nature. You just take the sum of all the sample values and then you divide them by the number of samples. For example, if you took 3 tests, you got 100, a 50, and a 0, then your grade is going to be a 50 because there's 3 tests. You have 100 plus 50 is 150 plus 0 is 150 divided by 3 is 50. The median, on the other hand, is not really so much mathematically found as it is just by counting. We distribute the data from smallest to largest and count up how many there are, and the middle value is the median, as shown below on the left. We use the mean as a description of the central tendency of a distribution on normally distributed data. We use the median when we're describing non-normally distributed data, stuff that's skewed in one way or another or has multiple modes instead of just one mode. When we describe quantitative data, we also need to describe how it's dispersed. We do this by the use of several different statistics, one of these being standard deviation, a similar statistic called standard error, and these two are used in pretty much in similar ways. Variance, which is used to calculate standard deviation and standard error, and these three statistics are used with normally distributed data. Then if we have non-normally distributed, skewed data or data that has multiple modes, we'll use the range, the interquartile range, and the modes. I have some formulas up here on how to calculate these. It's very simple. Also, when we talk about modes, data can be unimodal, like in a bell curve, there's only one peak. It can be bimodal, meaning it has 2 peaks. Or it can be trimodal or multimodal with lots of peaks. So these, depending on what you're dealing with, this is just some terminology you'll need to know. Many people confuse standard deviation and the standard error of the mean, and are unsure which, if either, to use when presenting data in a graphical or tabular form. The standard deviation is an index of the variability of the original data points, and that probably should be reported in all studies. The standard error, though, reflects the variability of the mean values, as if the study were repeated at a large number of times. By itself, the standard error is not particularly useful. However, it is used in constructing 95% and 99% confidence intervals, which we'll discuss later. And these indicate the range of values within which the true value lies. The confidence interval also shows the reader how accurate the estimates of the population values actually are. So if graphs are used, error bars equal to plus and minus 2 standard errors, which technically shows the 95% confidence interval, should be drawn around the mean values. Both statistical significance testing and confidence intervals are useful because they assist the reader in determining the meaning of the findings. When you display continuous data of quantitative nature, dot plots are one way you can do this. These are really the simplest form of graphical expression, and truthfully, they aren't really all that good. Patterns can get hidden and become overwhelming when you get a lot of these dots on there. And sometimes they just, when you look at them, they really don't mean a whole lot, especially when dots get superimposed. An alternative to dot plots is to use histograms for displaying continuous data. I'm not a big fan of histograms because you have to break things up into artificial categories in order to express them. However, they do work well in some cases. Uh, they allow you to make easy comparisons among histograms. Also, a unique feature of histograms and also bar charts, which we mentioned earlier, is that the width of the bar can be can be changed to represent a different size category, and that makes the histogram more representative of the data set that you're dealing with. Another type of plot that can be used is called a box whisker plot or a box plot. Uh, this is typically used with non-normal data, and the whisker is the range, while the box is the interquartile range, and the horizontal line that you see on each of these boxes represents the median. This is only used with non-normal data, and if you had normally distributed data, an appropriate alternative would be to use a point for the mean, and then whiskers to represent the standard deviation or standard error. In both cases, you can represent outliers with an asterisk or a star, and sometimes influential outliers will be further uh, indicated by using an alternative to a star or an asterisk so that you know exactly what you're dealing with. Scatter plots are similar to dot plots, except that there isn't a categorical type of expression on the x-axis, x or y-axis. In the case of a scatter plot, we've just got every data point plotted, and it can appear in many different places. Scatter plots are really good when you're dealing with data that's easily seen when distributed here, such as this particular figure I've shown you. However, when you start getting more than two compared variables, or you start getting complex associations, it becomes less useful and much harder to visualize using a scatter plot. To further demonstrate what I'm talking about, if you look at the upper left-hand graph here in this figure, you see that you can see that a lot of the red dots are a high on the y-axis, and the dark dots seem to be in the lower end of the y-axis. But beyond that, you really can't see a pattern. And that may be all they're trying to demonstrate. However, when we look at these other graphs, we start to see that people are using lines to try to show more of the depth and their relationships, or in the graph on the right, they've put a grid in to try to help you visualize this. It's not easy to decipher what's going on in these graphs, and that's why scatter plots aren't really the greatest way to display data when you're dealing with a lot of different kinds of different comparisons. Another way you can try to show multiple comparisons is you can use a whole series of graphs that show the different characteristics you're trying to compare. This can work really well if the different comparisons show up well on a single comparison like this. However, often it'll actually muddle the issue, or it can even show relationships that really aren't there once interactions are expressed. So I hope you recognize that there are many different ways to describe and to display both categorical and continuous data, and the real important thing is choosing the one way that will best tell the story you're trying to tell.